There are a couple of methods for putting a nitrile functional group on our molecule. The first one involves the standard SN2 type chemistry. We can add the nitrile as a nucleophile. The restrictions are this has to be primary or secondary. We cannot do this on a tertiary carbon because this is SN2 conditions. So we have a few restrictions. We can perform it on a secondary carbon. There is no concern about elimination reactions as the nitrile, the CN-, is not a particularly good base. If we wanted to, there's another way we could make a nitrile is to start with the amide, which has no groups on the nitrogen. And we can use SOCl2, and we essentially end up with something like this, plus SO2, plus 2 times HCl. The advantage here is that we can have anything right here. It does not matter what this is. So if I wanted this carbon to be tertiary, I could start with this particular amide, react it with SOCl2, and you can see here the only difference between the ethyl nitrile that I started with before and this one is that I've added 2 methyl groups to this carbon bearing the nitrile, and you would not have been able to make this particular compound using SN2 chemistry. This mechanism is very similar as carboxylic acids reacting with SOCl2 to make the carboxylic acid chloride. I'm not going to show that here, but you can definitely check that out in your textbook. So those are the 2 reactions that we can use to put a nitrile group into our molecule. We can either take an amide and dehydrate it, losing water to make the nitrile, or we can take a primary or secondary alkyl bromide or halide and use an SN2 reaction with cyanide. We can also react nitriles and form new functional groups from them. So if we have a CN triple bond here, we can react that with water and sulfuric acid, along with a great deal of heat, because nitriles are pretty stable. That triple bond is hard to react, and so we need strongly acidic conditions, high heat, in order to get this to react. And so what we're going to do here is basically turn this into an amide, which under the reaction conditions, strong heat, strong acid, we can't isolate. And so we end up with, as we saw on the reactions of amides, lots of heat, water, and acid will give us the carboxylic acid as our functional group. So we can basically take our CN triple bond and hydrolyze it to a carboxylic acid. So let's look at partial mechanism here. As we've seen with many fun with acid problems, we've got sulfuric acid. You should do something with the sulfuric acid before anything else. So we're going to protonate the nitrogen with the lone pair on the nitrogen as our first step here. This makes the CN bond a little more electrophilic. It can then receive the weak nucleophile, the water. We can attack the carbon just like we'd attack a normal carbonyl. So now we have this kind of interesting looking species. And remember that our goal is to basically install a carbonyl, so a CO double bond. In order to do that, I need to lose both of these hydrogens. So let's start proton transferring them away. I can use water to do that. And my goal also is to end up with NH2 right here, which ultimately then gets hydrolyzed to the carboxylic acid. So I need another proton on my N. I just gained one from the acid. So let's draw H3O plus again right here. We'll protonate that. This actually has some resonance, so I could draw a resonance structure. Now I've formed my CO double bond, I've formed the NH2, and if I can transfer one more proton, I have the amide. And so we've made the amide, and you've seen the mechanism of acid and water and heat, the acid catalyzed hydrolysis of amides to carboxylic acid. So I don't need to finish that part of this mechanism. That has already been shown. But this is how we would hydrolyze a cyanide group all the way to a carboxylic acid. So how is this useful? Well, I can probably summarize it a little bit in the center of my page here. So let's look at this option here. We could add cyanide to the primary alkyl bromide. And if I react the cyanide, or now the nitrile with water, strong acid, and heat, I know that the carbon becomes a carbonyl, and I lose the nitrogen, and I form a carboxylic acid. So what's the end result? Well, I've taken my 6-carbon starting material, and I've made it into a 7-carbon starting material. You should be able to come up with another way to take this primary alkyl bromide to a carboxylic acid that has 1 additional carbon. There's another way to do that. It does not involve chemistry of amides. So think about that and ask me for assistance on that later. We could also look at base catalyzed reactions of nitriles. They're going to give us the same outcome, except we just use different reagents. So maybe you've got something on your molecule that is sensitive to acid. You'd prefer not to subject it to strongly acidic conditions. Well, maybe you can use basic conditions to get the job done. And this is going to be very similar to what we saw for the hydrolysis of amides. I'm going to attack the carbon, pushing electrons onto the N. I have a negative charge on the nitrogen now. I need to add a proton there. When we're in strongly basic conditions, our proton source is water. Water is a weak acid. So this is a strong, reasonably strong base. So I'm going to draw water again here. I'm going to remove an H from water. And now I have a neutral compound. And remember, my goal is to form the CO double bond and to form the NH2, which ultimately can be hydrolyzed then to the carboxylic acid. So I need to remove the H from my oxygen now. So I'm going to proton transfer off this H again. That gets me to the O minus. I can draw a resonance structure which forms my carbonyl. And a negative charge on the N. I'm one step away now from the amide. And you can redraw that if it looks a little wonky to you. But of course, under strongly basic conditions and a lot of heat, our amide does not stick around. We cannot isolate it. We're going to immediately convert that to the carboxylic acid. And so that would be the end product. So again, just like on the previous slide, this is the base catalyzed hydrolysis of a nitrile. The end result is, again, a carboxylic acid. I would like to point out that you can contrast this mechanism with the acid catalyzed mechanism. This is basic conditions. There are no plus charges anywhere. I don't have any plus charges on my, my intermediates. They're all either neutral or negative charges. And my proton source comes from water. It does not come from a strong acid because that is impossible to have a strong acid in the presence of strong base. Lastly, some reactions of other reactions of nitriles, not just turning them back into amides and carboxylic acids, but could we actually make new functional groups from them? We have two interesting reactions to share with you here. If we react with a Grignard reagent and we work up under acidic conditions, we will actually produce, and I actually want to differentiate this so we can keep track of where our ethyl comes from. So this ethyl is added to the central, or the carbon here, and under acidic conditions we hydrolyze everything to make a ketone. How does that work? Well, we know that Grignards are good nucleophiles, so let's draw the nucleophilic attack on our nitrile. We form this compound, which is not reactive towards other Grignards. If it were to add another Grignard here, we'd actually put a second anion on the nitrogen. That's very unfavorable. So this anion just sits around and waits for the second step to happen, the acid workup. When we add acid here, this nitrile, of course, protonates rapidly, and we end up with, I hope you can name this functional group. Can you name that functional group? This is an imine. And under acidic conditions, remember we're in acid and heat, well, at least we're in acid with a lot of water around. Let's not call this heat. We're probably not working this up with heat. But the imine will hydrolyze rapidly to form the ketone. And this is a reaction from the aldehyde and ketone chapter, so I don't need to show you the mechanism of this step. This one we've already discussed quite a bit from the aldehyde and ketone chapter. And so basically the end result is adding a Grignard to a nitrile produces a ketone. So I think that's a pretty cool result. We now have a way to take a nitrile to a ketone. So let's look at another example of how this might be useful. Here's my other alkyl halide, and I'm going to react this with Cn minus. I'm going to react this with, and of course you can use just about any Grignard reagent. You're not limited to ethyl Grignard, certainly. So here is my new carbon that I added, and there is the ethyl group from the Grignard. So I've extended this carbon chain. It was a 1 carbon chain, now it's a 4 carbon chain by adding 2 pieces to it. I added the single carbon from the nitrile, and I added the ethyl group on the other side of that nitrile. So this can be a very useful synthetic tool as well. There's one more reaction with nitriles that I want to share with you, and that is simply reduction. We can take any CN triple bond, we can reduce it with lithium aluminum hydride, work up with mild acid, and we actually add a bunch of hydrogens to this molecule. We reduce the CN multiple bonds down to a CN single bond, and so we end up with just a primary amine. So again, let's look at our example. So we add cyanide, and then lithium aluminum hydride, and then mild acid workup. Here's my new carbon, here's my amine. So I can extend my carbon chain by 1 and end up with a nitrogen on the end of the chain. And then being able to make interesting amines like this one will be very useful for us in the next chapter when we study amines.